So we were of this opinion after looking at that example of triangle that we need to adjust in according to this specified criterion. That criterion which we discussed need to have certain basis. That basis which we discussed are the three possible. One is obviously the so-called sum of magnitude of all adjustment corrections to be minimized, adjustment correction with the maximum magnitude is to be minimized, and then sum of squares of the all adjustment correction is to be minimized. That is we call as the least square correction. So we arrived at this three possible suggestions. I'm again highlighting. One is obviously we must understand at this point that if you have an observation called Li, and if you are making a correction from most probable value for the set of observation, that become residual. So we were more interested in this part of correction. The corrections which we are highlighting here, the corrections which we are which we are highlighting here, this one, the corrections here is we are talking about the residuals. That residuals are nothing but the VI, which is individual observation and its deviation from most probable value, because we do not know the true value. Okay, so that is the corrections. People sometimes you may get confused. What are the corrections? What are those corrections which we are going to apply? So these are the corrections where we are having the set of observations and we just want to highlight the residual or the deviation of these individual observation from most probable. So one case is summation of all the observation is to be minimized. Then second is max of VI is to be minimized. That means we get VI 1 to let's say n up to n. So whatever value we are getting off of any value I, that is maximum, we want to minimize that. These are the two possible criteria. And then third is obviously the sum of squares of the residual to be minimized. So this is the basis of least square adjustment which we came into existence, is that what could be the specified criterion that we need to talk about. So that is one discussion that we concluded in our last class. Now moving ahead, what what would be the system of equation that would come after forming these suggestions? So ultimately, I had this solution of linear equations. What are those linear equations? First, like in your matrix, if you recall your BTech days, maybe probably be BTech third semester, where you have read about the matrix algebra, and you must have heard about the SK Das book, HK Das, sorry, and from where you have read about matrix algebra basics. And what we were doing, we were solving set of linear equations with the help of certain rules. Obviously, rank of matrix which we have computed so many times, that will be used here. So a set of linear equations, that is our system of equation that will be there. We will form such equation, and you will see that these equation will eventually be formed when we will discuss about certain examples today. So a set of linear equations, linear system of equation in n unknowns, would be given like this, and a coefficient Aij and constant Bi are known. So that would become the linear equation. Our objective is to find out the x. This is our parameter that we have to find out, but will be given with this equation. So how do we write it? We write it as a system of matrix as in a short form, which is Ax is equal to B, where A is your coefficient matrix, X is your unknown vector, B is your constant vector, and this is called as augmented matrix. Very generalized way. In your BTech, you write like that: A colon B. That is your way of writing of augmentation matrix. What is the role of augmentation matrix? It helps us in identifying or segregating the system of equation into certain other subcomponent to form out our solution. So system is called homogeneous, if the constant vector b is 0, and system is called non-homogeneous if constant vector b is not equal to 0. Obviously, these are the again same set rules which we have done in your BTech. But the problem is, uh, what is uh, what is the critical point here is that how your mind should understand that where we are going to form these equations, because that is important. Please remember what we are doing in our up till now. We were just looking at your chances of opportunities where you can adjust the data set. At the same time, you can get the parameters of interest. That was our identification of the problem. But here we are talking about the solution, but still we have not formed the equation. So just be patient, just understand the rules. Later on, we will discuss those set system of equations where we will try to form these equation like this. This a1x1 plus a2x2 plus a3x3 and so on. So that is the set of equation which you are going to form based on the question. So just wait and watch. So approach to solve this system is very simple. First, you will look for rank of the coefficient matrix, which is A. You think of rank of augmentation matrix, that is A is column V, and the dimension of unknown vector X. So because dimension is why the dimension is important, because the number of observation has to be more than the number of unknowns to get a solution. But in case if it is less than the number of observation, we'll see how we can approach the problem. So the consistent system and inconsistent system, we have two sets of system. The consistent system says if rank of matrix A is equal to rank of augmented matrix, and homogeneous system are always consistent. For inconsistent system, there is no solution for X. And then when this we talk about the inconsistent system, how it can be categorized further. So this table is prepared for you all. Just look at it. So there are three cases of non-homogeneous, two cases of homogeneous. Then value of constant vector is available to you. You just look at whether b is not equal to 0 or b is equal to 0. If it is b is equal not equal to 0, there will be three cases. Further, there would be a consistent case and there would be a inconsistent case. The consistent inconsistent case is where it is not equal to the rank of A. That means the augmented matrix rank is not equal to rank of A. Obviously, we do not get any solution, none. Then the second one is if it is consistent, that means it is equal to the rank of X. Then if it is equal to the dimension of X, you will get unique X. Okay. Similarly, the next one, consistent, but dimension is less than X, then we'll get the infinite solution to fit in that system. Similarly, there are two cases of homogeneous system, which is B is equal to 0 for two cases homogeneous. Then again, in that one, consistency should be maintained and the question will be asked on the dimension of X. It is less than or equal to X, obviously the unique solution in infinite case. And so the both two cases are possible for obviously the non-homogeneous system as well as homogeneous system. So these are the set number of rules to make sure that you should have enough confidence the moment you prepare your augmented matrix. And those who are not comfortable with understanding this slide, they should again go back to their matrix algebra basics, which you have done in your BTech, and just revise those basics. It is a prerequisite. So matrix algebra is your prerequisite for this course. From day one, I am telling you. In fact, I have uploaded the assignments also. So matrix algebra, you just need to revise and then you can quickly solve these questions. But the problem is we are not going to solve it using the matrix theory which we have read in our BTech days. We are just trying to solve it in a new conceptual manner, which we will discuss later on with this course. Today we'll start certain component, but the more will come in next few classes. Okay, so these are the theory which we need to understand that. Okay, one is you have a linear system of equation. You can form the coefficient matrix. You can form the augmented matrix. And at the same time, you need to understand whether my system would be whether my system would be non-homogeneous or homogeneous. If it is fall under non-homogeneous, then whether it would be consistent or inconsistent. Inconsistency can be simply by comparing the rank of coefficient and augmented matrix, which you can immediately do it. Rank is nothing but non-linear, linearly independent rows of that matrix, which is the one of the basic definition of the rank, which we have done. So these are the tables which eventually lead us to two set of solution. One is unique solution in case of the non-homogeneous consistent solution, and second is infinite solution in case of non-homogeneous consistent, but the rank of a is less than x. So these are the two possible cases. Similarly, these two possible cases are with homogeneous one also. So accordingly, we will prepare and we'll try to see whether we are achieving something or not. Okay. So with this, I think uh, yes, there is one more point about the uniqueness of the solution. That is, if rank of A is equal to rank of number of unknowns, that is number of linearly independent rows. So I would rather add here the rank would be called as the number of linearly independent rows. So for homogeneous system, this is a trivial solution. X is equal to 0. For a square non-homogeneous system, that means X would go to A inverse B. For non-homogeneous system having rectangular coefficient matrix A, that means more equation than the unknown, the matrix A transpose A is often non-singular and therefore has the inverse solution. The solution is given like this. That means you AX is equal to B is the way of writing your equation, the transpose on both sides like this, so that you could get X as ATA inverse ATB. So this is the rule which you must have seen in your BTech days. So the solution would be given like this for obviously non-homogeneous system. Then the solution which we discussed is called as least square solution and can be applied to obtaining the best average solution in the least square sense. Our next few discussion are focused on this because this is what we wanted, how to get the least square solution, because eventually we were concluding in this particular session is that the specified criterion is nothing but the summation of vi square is to be minimum. I gave you one question in the last class that I gave you one question in the last class is that please let me know is that how to derive that least square solution in the sense of how to derive it, whether the sigma vi square is the one which we are talking it, that we need to have this mathematical proof for it, because if you do not have the mathematical proof for this, then these are also equally applicable, applicable, isn't it? If you do not give the proof to this one, then obviously they are also applicable, and people will get confused that why you are going with sigma summation vi square is to be minimum. In fact, if you have this vi summation of vi is to be minimum is also there, one of the criterion, one of the possible criterion, and then you have max vi is to be minimum, that is also another possible criterion. So any of you have given a thought over it, how to derive this, because this is one part which we wanted to discuss. Obviously, we are going to discuss next the same, but I wanted that, have you given a thought? Anyone could just give me some explanation on it? Alok.
सर नहीं किए, नहीं किए हैं सर।
क्यों भाई? नेक्स्ट क्लास भी नहीं हुई थी, लास्ट क्लास, तब क्या कर रहे थे पूरे हफ्ते भर?
सर क्वेश्चन के बारे में भूल गया था कि ये करना है।
अच्छा चलो, कैसे अप्रोच करोगे? मान लो अभी दे रहे हैं तो वैली शेट्टी आप बताइए।
Sir, I didn't do, sir.
See, I'm not interested in not knowing. I'm interested in how you approach it. If now I'm giving you the problem, just think of your possible options which are available to you. Just think in that direction. For what purpose we are reading these content? The first reason is obviously to remove or reduce the random errors, isn't it? That was our initial. For all, I'm just telling you, for all, just think in that direction, that why we are reading these contents, because we have, from first lecture onwards, we were of this opinion that systematic errors can be mathematically solved, gross errors can be ruled out by certain thresholds, certain rule of thumb. But about the random errors, we do not have any specific methodology, isn't it? What we have, in fact, in our hand is probabilistic approach, by which we can have an idea about their probability of occurrence, isn't it? This is our whole soul summary. In order to remove the requirement to remove random error is there because you get inconsistent solution, and we have seen that in our previous lecture. That means we have got 5 observation, we have to find out one unknown, and we have 9 ways by which we can find out x, and for every case x is getting different values. So that is, we have seen the inconsistency in the solution. The reason is simple, because you have the randomness in our data set. Your observations are containing errors, because of which you are getting different x. So your one available option where you can explore is the probabilistic model which you have in your hand. So just think of your model, how you can write the probabilistic model for random errors, not for observable, because for observable it would start with 1 upon sigma root 2 pi and everything. But for Gaussian errors or random errors which are behaving in a Gaussian nature, how do we write the model for that? First, you think in that direction. That is the hint. Now, if you just think that if one random error in observation can be represented by this equation, what about the all possible random error that are occurring together? Because it is not a system where one random error will occur after another. In fact, this is a system of a reality where all possible random error will occur simultaneously. So how do we find out the probability model where we take the probability model for random errors that are occurring simultaneously? So just think in these two model direction, you will get the solution. I'm again giving you 5 minutes. Just think in that direction. Do you have, in fact, you have in your previous lectures, you have the Gaussian error probability model where you have used H. Just think of that slide. You can in fact go back to those slides if you have the notes. Just think in that direction and then let us know. Because if I just show the slide that this is the solution, your batti would not come out. Your mind should think in that direction. Then only you will appreciate the solution. So I'm giving you a little time. Just think in that direction, and probably most of you would derive the same very quickly, because it is simply you have to minimize the sum of squares of the residual. What are the residual? That would you have to identify in that model. Because until unless we do not derive it mathematically, and if you do not understand the derivation, you will not appreciate the further steps. Because every time in your mind, you would always realize that why we have not adopted the max of vi is to minimum, why we have not adopted the summation of vi is to be minimum, why we have chosen this summation of vi square is minimum. This is a very basic question. बताइए भाई. सुमित.
यस सर.
हम्म.
सर अभी ये चैप्टर सर समझ में नहीं आ रहा. एक्चुअली लास्ट क्लास मैंने ली नहीं थी, रिकॉर्डिंग मैंने 1 घंटे तक ही अभी देखा है सर. अभी मुझे समझ में नहीं आ रहा है सर.
हफ्ते भर क्या कर रहे थे भाई?
हफ्ते भर क्या कर रहे थे भाई? सर एक्चुअली असाइनमेंट वगैरह मिला हुआ है, जीआईएस का टेस्ट भी है, तो सर थोड़ा सा स्किप हो गया था मुझसे।
ये सब मैंने डे वन से बोला हुआ है। आई विल नॉट एक्सेप्ट दीज एक्सक्यूजेस,
यस सर, यस सर,
है ना?
सॉरी सर।
If you are not giving weights to this class, you would not be doing justice to your curriculum.
नहीं सर, सर वो मैंने वीडियो
It
देख
is
like
not 12th
रिकॉर्डिंग।
level, na? You cannot say like I have exam of history, so I'll forget about maths.
यस
That is your irresponsible statement. Anyways, so we are in a domain where we have to justify our adjustment approach. So first is assume that errors are normally and randomly distributed. The principle is derived from normal law of error or Gaussian law of errors, and then from the principle of maximum likelihood approach, that is the residual errors between the original and adjusted observations is assumed to be the most probable set of measurement. That means the corrections, the set vi, which is the residual vector or residual errors between the original, that means the given observable, and adjusted observations is assumed to be the most probable set of measurement. The probability of measurement lying between vi and dvi is given by this equation. This is very basic equation, that probability that v would take value between vi and vi plus dvi, which is given by the way that 1 upon sigma root 2 pi and so on, where some expectation of the error is actually the zero. That's the mean is converted to zero, and your xi is replaced by epsilon I. That's why you are writing this, or epsilon I. You can also, for better approximation, you can write this expectation of residual is to be zero, because they are same. The error or residual both are the same thing, and xi is now replaced by vi. So now you can change this equation to this, and probability of observing v1 in dv1, v2 in dv2, and so all possible error sources, you get the all possible possibility multiplied together. So this is the multiplication sign, just like this is a summation sign, this is the multiplication sign for all possible probabilities that are occurring between vi and dvi. So this, you get this kind of multiplication. After multiplication, you get this kind of solution where all HIs are multiplied with this exponentially. They are all added up. The summation comes here because they are in the power term. So they would all be added up. And here also the all partial derivatives are dv1, dv2, d3, dv3, and so on. In fact, if you take the integral also, it will go like dv1, dv2, dv3 like this. But what you need to understand right now, if everything is constant, because h is also constant as I've written here, so what is behaving? So you have a e ki power minus x curve would look like this, isn't it? So curve is approaching or asymptotic to this x-axis and go on moving. So you will achieve the maximum value. That means the maximum would only come when this minus term would get maximized, isn't it? If this minus term would get maximized, then you will get achieve the maximum value, because this has to be minimum, the maximum likelihood at max function. So if minus is going for maximum, then positive would go for minimum. Sign immediately convert if you multiplied with my minus sign. So if this is going for maximum value, then obviously the opposite of it would go for minimum value, where h is constant. Now you have a very decent proof where summation of vi square is to be minimum for maximum likelihood estimation of all possible error sources. So L is the maximum likelihood estimated value for which if this goes to minimum, this would achieve its maximum value. Okay, because maximum would come here, isn't it? So anyways, this is the mathematical proof by which we are arriving at this solution of summation of Vi square is to be minimum. Okay, so it's very basic because I've given you every basic equation in your previous lectures. These are the probability values which you are very much familiar for how to write this partial this PDF equation for individual error sources and individual observation. So for those who are still getting little difficulties, how would you write? How would you write about the PDF of any observation? You will write 1 upon sigma root 2 pi exponential x minus mu by sigma square 1 by 2. That's how you will write, isn't it? And this is the partial derivative equation or PDF for observable. Observable as xi. But here you are talking about the errors. So this xi would become vi. Okay. But this mu, so that means expectation of individual residual. What you expect from your errors? They should be zero. The mean should be zero. They should not be having any values. You want them to be out of system, flush out of the system. That's why their mean value should be zero. And the h is nothing but 1 upon 2 sigma I square. So you can convert this immediately to this function for an individual first case. That is uh, probability that error is within a very small error interval, which is dvi. Similarly, if you want all possible random errors of the system at the same time, what you want, the maximum likelihood function would take place. An error model of all possible random errors would be written in this fashion, where probability models of every error sources are multiplied together. Please remember or recall the example of dice which we have given you. The two dice flown together. What is the possibility of head? And the boxes, if you draw red ball from one box and red ball, the ball from two boxes, and possibility of it become red. So for these all possible cases, what we have done, the probability of union, probability of all possible chances that would arrive at the same time, we have just multiplied it, isn't it? So for that, uh, we were doing it, and in that case we arrive at this similar function of exponential minus summation of hi square vi hi square vi square, and we have seen that function is can be maximized only if this value is maximized and their minus value is maximized, so opposite of it to be minimized. It's very straightforward. I mean, if you understand the theory, you can quickly relate to it. There is no problem. So I hope it is very much clear. Okay, so what are the implications? Implications are very much simple, that most probable values are obtained if errors are normally distributed. So these are the implications which you need to understand. And if errors are just symmetrically distributed, the unknown parameters to be determined have least mean errors and maximum weight. For any kind of error distribution, LS has advantage of giving unique values with least computational effort. Please remember, at this point, if you do not appreciate it, is no problem, because at the coursework, what is generally happening, people just read about the approaches and then forget about it. That you won't believe that one of our PhD student have just used least square model, just use the basic least square model that are being taught in the classes, and have solved two basic problems of GPS network strengthening. That means a established network is there already, and and he wanted to establish the network by three more points. So the location of these 3 points has to be given in an optimal manner. And that optimal values of this position of the rover receiver within that box is given by least square solution. It's very problem is very simple. You have a network of stations around a place and you want to strengthen this network by 3 more GPS stations, but you do not know the location of it. Where do you place it? So you made a box, the search box, that the position could vary between this only because of certain topographical constraint as well as the limitations of the GPS approach. So the value of the values of the boxes are given to the model, least square model, and the model finally gave the answer as where we have to find out the so-called where we will get the optimal values of station to be placed, and that has been placed at one of the journals of uh, American Society of Civil Engineers, Journal of Surveying Engineering. So you can find it out. A very basic problem, but it has been solved by least square. Then again another problem is again very simple. In your one of the remote sensing domain, we have a microwave remote sensing where you read about the one of the advanced technique which is called as INSAR, interferometric synthetic aperture radar. So interferometry, we use the phase values of two observations for ith image and for jth image. When you subtract these two images, you will get a interferometric pair, which we call it phi ij. Similarly, if you have this values of phi ij from I is equal to 1 to n, j is equal to 1 to n. So you have lot of huge pairs from an image, and these pairs would go into a least square system and would eventually give us the master pair value like I to 0, 1 to 0, 2 to 0, 3 to 0. They are just uh, solving the giving from all possible pair to single interferogram pair. So now at this stage, you will not appreciate the advantages of least square, but it is solving variety of problems. Many of the complex problems are solved by least square solution very quickly. So the model has that much power, which we as a scientific community appreciate it. So you can apply it to variety of equations. Obviously, these implications are just to tell you what is the importance. So most probable values are obtained if errors are normally distributed. If errors are just symmetrically distributed, the unknown parameters to be determined have least mean errors and maximum weight. For any kind of error distribution, LS has the advantage of giving unique values with least computational efforts. Least computational efforts means any other model would be taking too much time in getting the solution, but least square solution is very quick if you have found the right pair of equations. Okay, so principle of least squares in a case of matrix manner, we'll explain it to just a moment. Yes, so we have residual vector, which is v, that is nothing but v1 to vn, maybe v2 or vn. So let's say take it as n. Then you have a weight matrix. Weight are associated with observation. So P1, P2, P3, Pn. Then you have the function. This is your function, desired function. The summation of Pi Vi square is to be minimum. Now the question is, why do we write V as V1, V2, V3, and Vn? Because residual vectors are vectors that are associated with the observations. So observations are what? Observations are Li, that means L1, L2, L3, L4, and so on. So you have set of vectors, isn't it? Observation vectors. And when you do minus MPV, minus MPV, minus MPV to each observation, what you will get? you will get the residuals, isn't it? So that's why the residual would have the same vector as the vector of observation. That means if observation vector is written as n cross 1, residual matrix would also be written as, or residual vector is also written as n cross 1. Very clear? Second point is your weight matrix is always associated with observations. Please remember, I have told you many times in the previous classes also, your residual is your, sorry, weight matrix. Weight matrix means how much weights you are given to a particular observation is always, the weight matrix is always associated with observation. So it would become a diagonal matrix because it would be having relative values of P1 to P2, P2 to P3, P3 to 4, P4 and up to N. So it would be a diagonal matrix. So it would become n cross n. Fair enough. You have a function of least square where either you write summation of vi square is to be minimum if all weights are equal, and if weights are not equal or different weights are assigned to different weights, so you will write the least square solution as summation of vi square is to be minimum. Many of you would ask, sir, why the residual vector is multiplied by weight matrix? Because very simple, your weights are associated with the observations. Observations are having residual or errors. So weight would be multiplied with residual only. Why? Because if you have to form the weighted mean, what you will do? You multiply weight with the observation. Here we have to minimize it. The correction, the correction would also be applied in a weighted fashion. So weighted least square, isn't it? Just like weighted mean, where you have to minimize the error sources. But if you do not consider their weight, what will happen? The higher quality data would get same correction to in comparison to the lower quality data that you do never want, because you want that the quality of the data set should be considered while adjusting the data set. Please remember. So I hope you understand this point. If you have any query, this is the right time you can ask, because I don't want that any sort of confusion to move forward. If you have any query, you can simply ask here. Anyone?
Sir, in last line you said that the high quality data should have not same with the low quality data. Sir, what was that word particularly, sir?
See, if somebody have queries, sir, you have up till now you have discussed about this, okay, about summation of vi square is to minimum. Then why we are using this as a now new function? The answer is for that is, if you have observed, you will weights, because weights are integral part of your system. So if you are having weights of individual observation based on the precision of the data set, if a data is of highest possible precision, its weights would be higher, and you cannot compromise, you cannot ignore. In fact, if you are given the weights, you will approach with by this method only. That means weighted least square approach. Why? Because if you ignore the weights, what will happen here? You would be given correction without considering the weight of the individual observation, without giving weightage to individual observation. Okay. So what are the possible circumstances? or consequences? The consequences are that if you do not consider the weight of any particular observation, you would be applying correction as if nothing weights are available. I mean, every observation has equal weightage. But in fact, in general sense or in practical sense, what is really happening? Your observations are, some of the observation are very precise, some of observation are very less precise. But corrections would be given equal to every values, which you do not want. You want that correction is to be proportionate according to the weight. You get it?
Yes, sir. Now, okay, sir.
So you make that function y is equal to summation pi vi square. But now there is a little correction, in the sense this is your uh, I mean, way of writing in a single dimension function. But how do you write VTPV in matrix fraction? That is one point which I wanted to discuss right now. Because if you understand this part, just tell me why it is VTPV and why not it is VPV transpose. That is my question. We have written PV, but why it cannot be VPV transpose? Any answers for that?
Matrices will be not compatible.
Sir, for matrix compatibility reason.
क्या समझाओ उसको बताओ तो.
Sir, if P is suppose n cross n matrix and V is n cross 1 matrix, then for multiplication purpose, if we put it like sir,
नहीं तो अब
sir,
आप इस वाले केस में देखिए V की साइज क्या है. V की साइज बताइए.
sir n cross 1,
N क्रॉस 1. P की साइज बताइए.
sir n cross n,
N क्रॉस N. और V ट्रांसपोज क्या हो जाएगा?
so 1 cross n.
1 cross n.
1%. तो कुछ कंक्लूड हो पा रहा है इससे?
सर ये नहीं बन पाएगा, मींस कि ये
नहीं बन पा रहा
मल्टीप्लाई
है
नहीं
ना.
हो पाएगा. यस सर.
मल्टीप्लाई नहीं हो रहा, इसलिए पहले
सर ये
मिनिमम आप
बहुत
क्या करते हैं जब आप ऐसे लिखते हैं किसी फंक्शन में मिनिमम, then what you do, you try to minimize a particular value that is coming as a certain value, isn't it? In a iterative fashion, what you want that this value which is coming here, this value is going to be minimized, isn't it? So when I say summation of vi square, that means after squaring these residuals, when we add up, this would give us a value, single value. It is a value cross 1 cross 1. It is a value, not a matrix. Therefore, VTPV suggests V transpose 1 cross n, P is n cross n, and V is again n cross 1. That would lead us to 1 cross 1. That's why we are writing VTPV, not VPV transpose as minimum for in a matrix fashion. Is it clear now?
यस सर.
Anyone else having any doubt?
सर अगर डिटरमिनेंट टर्म में होता तो का नाम ट्रांसपोज लास्ट में लगा सकते थे.
कौन बोल रहा है?
प्रवीण.
प्रवीण, क्या कह रहे हैं आप?
सर अगर मतलब मैट्रिक्स अगर डिटरमिनेंट फंक्शन में होता तो हम मतलब वीक ट्रांसपोज लास्ट में निकाल सकते थे, बट इन्हें मैट्रिक्स सर्फेस मल्टीप्लिकेशन में ना हो पाएगा.
सी अभी उस स्टेज पे जा ही नहीं रहे. अभी तो हम सिर्फ ये देख रहे हैं कि मेरे पास डेटा आया है, मैं उसको अरेंज कर रहा हूँ और एक मैट्रिक्स सोल्यूशन की ओर बढ़ रहा हूँ. फॉर मैट्रिक्स सोल्यूशन वी हैव टू फर्स्ट derive the function or write the function, the basic function. The basic function is for any kind of adjustment operation is summation of vi square is to be minimum, and that vi square is to be minimum has to be written in a matrix fashion. Why? Because data in your coming few examples would be very huge. It cannot be you cannot gather the data in a single dimension. It is a multi-dimensional data that would be coming to you. Then you need matrix way of writing it because you have to solve it. So when you understand the n number of observation that are coming to you, then you will write n cross n as a weight matrix, n cross 1 as a residual matrix. Then how do you write the function? So for writing the function for least square, we write as phi is equal to VTPV. That is the same as in linear dimension, we are writing as summation of vi square. Okay.
Okay, sir.
The assumptions for the least squares is that you need very large number of observations. There is a very basic requirement for least square adjustment. Please remember, you do not go with the least square adjustment with merely 2-3 observation or 5 observation, 10 observation. You need a large set of observation. That will only be possible when you work with any instruments. It is not possible to apply least square solution to your basic problems. Basic problem is generally solved by your the basic linear system of equation. The moment you have large number of data set, why? Because why do we need large number of observation? Because principally in your first class I have told you the histogram you have to avoid it. You have that much data that will represent as a smooth bell-shaped curve. That will only happen if you have large number of data set. Okay, so you do not work with a discrete kind of data set. You work with a continuous data set that has a huge number of population. So that is the assumption for least square solution. One is very large number of observation. Then second is symmetrically distribution. Sometimes what we have found is that if your data set is not symmetric, then also least square gave a solution. There is no problem. But for our case, in Geo-Informatics case, sometimes symmetry is preferable. We need symmetry. Then uncorrelated observation. Every measurement is exact in nature. That means are uncorrelated with other measurements. Okay, so measurement should be uncorrelated. There should not be any correlation between two measurements. And either arithmetic mean is the most probable value or solution with the smallest sigma for symmetric distribution. So these are the 4 assumptions that you should remember. Let us quickly go back to discuss about some of the assumptions for least squares. One is if any of the assumptions which we have discussed is not valid, then other methods of adjustments are equally sound, which we have discussed in the previous class. No issues. Main purpose of adjustment is to have geometrical and physical consistency, and LS has also have also other advantages such as error analysis that we'll discuss. That means please remember in our first of the discussion I've told you, if you are going ahead after MTech, let's say if you are going for PhD, so and in fact in MTech only people are not interested in your final solution, isn't it? People are interested in your uncertainty in your data set. That means if you are saying that I have performed certain analysis over this data and achieved this, people will never ask about the result. People will ask about the error distribution. What are the error analysis? What are the uncertainty in your data set? Let's say you have prepared the DEM for a particular region with by some techniques. Let's say anything, whatever you can think of. So people will not ask about the values of a particular resolution element. People will be asking about the errors involved in that value. Let's say if it is you saying that this pixel is having 10-meter elevation value, so people will not be interested in 10-meter how you achieve 10. People will be interested in what is the errors that are available in that 10-meter, whether 10 plus minus 5 meter, 10 plus minus 2 meter, 10 plus minus 10 meter, whatever it is. So people will be more interested in what are the error distribution, which the error part involved here. And that's why in least square adjustment, this is a inherent advantage that if you perform least square solution, automatically you have advantage of performing the error analysis. That will show it later on. To minimize effect of random errors, we have to collect many observation more than what we need. That is called a redundancy. These extra observations are called as redundant observation. Okay. The only way to get unique solution and the best is to adjust all observation. Now this is very important. Why this is important? Because you have seen this triangle problem of last class where you have to find out the distance between 2 points A and B, but you have got 5 observations and you have formed 9 set possible the so-called combinations. Okay. What least square will give you is that it will take into account all 5 at the same time, irrespective of what they goes into the model and what not. Just think of is that you know the equation as cosine rule, sine rule, tan rule, whatever it is, but you work with previously you work with only those set of observation which goes into that system, isn't it? Alpha 1, alpha 1, d1. So you that in that case you work only with cosine rule. Then alpha 1, alpha 2, alpha 3. Then you work with the summation of triangle. Inside triangle is equal to 0. But in the least square, what we are doing is we are working with all possible solution, all possible observation, and that all are going into that system of least square together. This is one of the major advantage that is written here in this case. The so-called the box which we have written is that the only way to get unique solution and also the best is to adjust all observation in such a way to eliminate that discrepancy, inconsistency while following one of the approaches says least square. That means that system which you can think of that LSQ is a system, all possible observation at the same time. They are all going into that system and finally giving you the X, irrespective of the model. That your least square model is going to take care of how to handle that all such observations. This is the beauty of it. You do not have to think of individual equation at a time. Your model is enough to capable of, but obviously these equation will be part of here, and you will see that how we are going to do it. What are the properties of least square adjustment? These are the properties. One by one, you can read it out. It is that you should quickly go through it once a time. It is oldest, originally developed in 18th century. Most rigorous of all adjustment procedure, applied with greater ease, enable rigorous post-adjustment analysis, used to perform pre-survey planning, measurement adjusted using procedures that conforms to the law's probability, provide most probable solution, allows individual weighting, forces geometric closures, provide estimated errors, simultaneous adjustment, provide single solution, that is our objective, can be programmed on computer. And that's why you are having this MATLAB initial lectures, because that you can program it to find the solution for a particular case. Just go through one by one. If you have any query, you can ask.
Sir, what is meaning of
हाँ
forces geometric closures?
हाँ, कहाँ पर कौन सा पॉइंट?
Forces geometric closures.
हाँ, फोर्सेस ज्योमेट्रिक क्लोजर का मतलब क्या हुआ? इफ यू डेवलप ए नेटवर्क, that means you go from first to second point, second to third point, third to fourth point, fourth to fifth point, and then you come again and on the first point you will never reach. That is the reality of the world, because if you go by from the observation point of view, you are, irrespective of your accuracy, efficiency, you are committing random errors in your observation, and because of which you never achieve or reach the first point from where you have started. Is still you always have a certain misclosure in closing that loop. आपने वोल्टेज में किरचॉफ लॉ वगैरह सब पढ़ा होगा ना in your preparation for JEE. In that we have a loop, and every time we make inside the loop, we will always V12 plus V12 then minus V13 is equal to 0. But in our reality, it never happens. It never goes to 0. That's the reality of the world. So least square will provide the solution to individual steps. That means from 1 you are going to 2, then from 2 to 3, 3 to 4, 4 to 5, 5 to 1. So for each these steps, solutions or corrections would be provided to you such that you will, after correcting, you will reach to 1. That is ensured. So that's why it is called as forces geometric closure. What do you mean by geometric? Many times people do not ask by considering that they know what do you mean by geometric. But if I ask you, all of you would have certain incorrect understanding of geometry. Geometric term is nothing but, is not about the geometry that you have read about. It is all about the values, numerical values, where you measure distance, you measure angles. The moment you measure angles, you are in the geometric sense. The moment you are measuring distances, you are in a geometric fashion, you are doing it. So that geometric sense is preserved. Any other question? Okay. So these are the three possible solutions. How do we write it? Obviously, I'm just enlarging it a bit so that you could understand this. From the left hand side, what we have, L sigma L. Now this L is number of observation or a system of observation which you are having. Sigma L, obviously, we are from the day one, we are not moving ahead without error matrix. So L is your number of observation, maybe a vector of n cross 1. Again, this L is n cross 1. Then obviously corresponding variance covariance matrix would always be n cross n. So your sigma L would always be n cross n if your vector is n cross 1, because it is a square matrix. Okay. What you want, you want to reach from L sigma L to X sigma X. That is our objective. From L sigma L, you want to go and achieve X sigma X. The parameter as well as the associated matrix. So let's say it is your X is U cross 1, then sigma X would be U cross U. This is our basic understanding of least square model. Very good manner by which we are writing it here. That means from L sigma L, we are reaching to X sigma X. Is there any problem in understanding this equation? Because if you do not understand this, then there is a problem at this stage. So those who are not picking it right, they may ask the question. This is the high time that you should ask the question. because this is our initial step, the baby step, which we are just starting, because next 4 or 5 classes will be complete models, associated equations, and I dare you not to miss those classes, because even in the recording also, if you have query, you cannot ask. So do not miss the classes. Enjoy it. Is very good set of equation you will be given, and you can solve any problem in the world, any problem. Very basic equations, very small, simple equations, and you can solve anything. Obviously, with this basic equation that you go from L to sigma L to X to sigma X. Anyways, okay. So we have 3 objective to find X and corresponding covariance matrix. What we want a solution that implies in a general sense getting pair of X, sigma X. And what we need to do, we need to solve a mathematical model, which is equivalent to seeking transformation from observation space to parameter space. What do we mean by observation space to parameter space? Let us see that. So okay, so these are the questions that will start, and we will go back to look at the function, how the functions can be written. If it is explicit in X, that means X is clearly written as function of L. Please remember this part I'm talking about. You start your work and you ask a question whether in this question X is given as a function of L, or X is the linearized version is X is equal to GL plus W. You can, if you say yes, then it's okay. If it is no, then linearize it. Non-linearizable, non-linear solution, linearizable, you linearize it. Anyways, the question is very simple, explicit in X. अब आप कहेंगे ऐसा कौन सा function होता है where X is given directly as a function of L? आपने solve किया है function. Please remember, I have asked you to solve for H given the slope distance D and a vertical angle alpha. You have written H is equal to D, or so-called how do we write it? The sine alpha is equal to H upon D. The H would be D sine alpha. That's it. D is your observation. Sine alpha is your observation. What you want H. That means function is explicit in X. So there are a lot of functions where you can write this equation as X is equal to function of. This is just a simple flow chart to tell you whether you are going in the right direction or not. So if it is yes, you go ahead, find out the solution. If it is no, then you will see whether it is a linear model is there or non-linear model is there. How you can write those models. So it is linear, answer is yes or no. If it is no, you think of linearizing it. If it is not possible to linearize, you go back to find a non-linear solution. If it is linearizable, yes, you come back here. Then you again ask question, because here it was no. Again you will ask whether it is explicit in L. Then you will write like this: L is equal to Hx plus W. Then again you will ask it is explicit in X, L or not. If you say no, convert implicit to explicit form. I'll discuss all these models one by one, but these are just way of explaining the models. Okay. Anyways, models that cannot be linearized usually require different techniques for their solution. Treatment of a model is based on form, linearizability, determinacy. And model explicit in X, that is U is equal to number of unknown parameters. You will only complication is in getting the sigma XX. Anyways, just forget about these theory etc. At this point of time. Just understand this point. Either you get the unique solution if n is equal to u, you get the undetermined solution if u is less than n, and you get the overdetermined solution if n is greater than q. Then you will solve these problems. Okay, anyways. Before discussing this, let me just take you to one figure, very good figure, which you will appreciate. Just wait a minute. This figure is not available here. I missed the figure, I guess. Oh, I guess we missed the figure. There is one figure, I guess, where it is. Anyways, that figure is very nice example of relating the observation space to parameter space. Anyways, I'm just switching the so-called to next EDA. Just wait a minute. Just okay. So I hope it is visible to all of you. So
Yes,
what
sir.
we are going to cover now, first we will discuss about these. The basic introduction to differentiation of vectors and matrices. So when I say least square model, that is we are where uh, the least square model, which is taking input as L as sigma LL, and it is coming giving X and sigma XS. We are talking about this, isn't it? Where we are inserting this L and sigma LL, and we are getting this X and sigma XX. This is our system. But how the LSQ, which is least square adjustment model, how we can form these models? So they are formed in three manners. One is called as observation equation model, another is called as condition equation model, and another one is called as mixed model. So there are three types of model that we are going to discuss in this course. One is observation equation model, another is condition equation model, and third is mixed model. So you could see here, we are going to discuss the observation equation model and all set of related equations. Then we'll discuss the geometric interpretation, calculus view, then we'll see the characteristic, and then some examples, the iterations and the observation strategies, and obviously the examples. The six would be examples. So we are first focusing on the observation equation model. But before going to that observation equation model, we need to first understand how the differentiation of different vectors and matrices is going to take place. Please remember, in your Jacobian, I have told you many times that Jacobian goes in number of function, number of variables. So del f by del x1 goes up to del f by del x, and then here you go del f n by del x1 and so on. So we are just revisiting those partial derivations and calculation for better understanding. So that's why in this content we first focus on this part, okay, this differentiation aspect of vectors and matrices. So we'll first focus on observation equation. Second, in next few lectures, after maybe 2-3 lectures, we'll come back to condition equation, and then after that we'll discuss the next one. So there are 3 models. Inside that we are inserting these observables. Okay. So first is quickly we are moving towards introduction to differentiation of vectors and matrices. Okay. See here, the vector x whose elements are function of u. That means there are how many functions? I mean, there are we have a vector as x and whose element of function of u. Okay, so x is written like this: x1, x2, x3 up to xn, and transposed by why? Because it is written in this manner, like this. But to make it less spacious, we make it transpose at the last. That is the way of writing. Anyways, so you have x like this, derivative of x with respect to u because it is a function of u. So dx by du would be written as dx1 by du, dx2 by du, and so on, dxn by du. Differential change dx of vector x is written like this. Then if elements of a matrix A are function of the scalar variable u, then the derivative is written as dA by du as dA1 by du, dA1n by du. Similarly, dAm1 by du, dAmn by du. So these are all way of writing. Again, just if you have little difficulty, and just quickly recall every single equation which is written here. For a vector x whose element of functions of u is whose elements are function of u. There's a little typo, a function of u. Okay, so x is written like this, but when you write partial derivative with respect to u, because they are function of u, that x is a function of x like this. If it is written like that, okay, or x1. The x1 is a function of u, like that. So you derive it with respect to u, the whole x. You will write dx1 by du, dx2 by du, dxn by du, similarly like that, isn't it? Similarly, if your differential change of vector dx would be written as dx, dx1, dx2, dx3, dxn. If you have an element of matrix A, which are function of the scalar variable u, then the derivative of, again, same to this, but in a square matrix fashion. It's very basic, nothing critical. Then you have another query. If a vector y, which is m cross 1, represents m functions of some or all of the elements of variable x, size n cross 1, then the total differential of y would be given as partial derivative plus dx. So this you have done in your BTech. So del y by del x, that is your partial, multiplied by dx. Similarly, where total differential dy and dx follow the definition given earlier, like this: partial derivative of y, we have partial derivative dy by dx given by this. So these are the ways you can quickly recall your basics. For the expressions A independent of y, v is written as m cross 1, A as m cross n, y as n cross 1. But A is independent of y. So when you write dv, so it will be written as dv by del v by del y multiplied by dv, which becomes m cross n multiplied by n cross 1. You will write v as A. So A would come out as a entity. So A would be del ay by del y would become A. Similarly, w B independent of X would be written like this. If it is written like this, W would be. So these are the basic way it is represented. And there is at present it may look like little different to you, but when you go back and try to revise it through your basics of partial derivatives as well as the total differential as well as matrix algebra, it will be very straightforward. Okay, anyways. Similarly here, bilinear form and quadratic forms are given. So you can see it. There is no problem in that. Very straightforward. Bilinear form, quadratic form. Okay. The notations which are very will be used in this coming few classes. Take one by one notations. You just understand one by one. One is n, small n would be used for number of observations. LB will be used for observed values. LA or L hat will be used for adjusted observables. Capital X for parameters. X hat or XA is for estimated or adjusted value of parameter. V, that is LA minus LB. Sigma naught square, a priori variance of unit weight. Sigma naught hat square, a priori posteriori variance of unit weight. P, weight matrix, where weight matrix is written as QLB as P inverse. Sigma naught square P inverse is equal to sigma naught square QLB, and this is all we have done in your previous classes. It's again same. Now just stay back here up till now. Again, quickly understand what is there in your system of equations or in your problem. What you are having. You have in your field. You go with the instrumentation. You know, in your field, you go with your instrumentation. You collect observation. Observations are n cross 1. That is first thing. That is the first. Your observation have dimension as n cross 1. These are the notations which I am explaining that will be used in coming slides. That's why I'm explaining it before. N is number of observables, number of observations. LB is observed values. The values of all these n's, what you will give, will be given by a vector called LB. LB is having size as n cross 1. So LB would be a vector. Vector size is n cross 1. Why? Because your number of observation are n cross 1. Okay. Second is these observations are containing errors, and when after adjustment you are representing it, you will represent it by LA, that is adjusted observation, or L hat. There is a term called L hat which you will be using. L hat will you call it as adjusted observation. X, capital X is your parameters. Please remember in your linear system of equation, what goes in Ln sigma LL. What goes out Xn sigma XX. What is the size? Size of L, which is written as LB, is n cross 1. Size of sigma LB or LL simply n cross n. What is X? Parameter size U cross 1. What is sigma XX or XA would be U cross U. That's very simple. Very straightforward. What is the dimension of X? U cross 1. What is the dimension of L or LB? N cross 1. Correspondingly, you will have variance students matrix as square matrix. If it is observable, n cross n. It is of parameters, u cross u. Then x hat or xa is nothing but the estimate or adjusted value of parameter. Again, size u cross 1. Residual la minus lb. The residual is always. अब आप कहेंगे residual सर आपने बोला था vi is nothing but l minus mpv. So after adjustment, what you are getting? After adjustment from least square, what you are getting? You are also getting LA and sigma LA. So L is adjusted now. The adjusted value and the best value. So now it is replaced by your called LA. So here it is written as LA minus LB. Sigma square, a priori variance factor. Sigma naught hat square, a posteriori variance factor. And P is weight matrix. That means weight matrix PLB inverse is equal to QLB. That I mean, these are all in your previous classes from where we are taking it. That means the inverse of weight is cofactor matrix. Then posteriori a priori vector variance reference vector multiplied by weight inverse is now your so-called variance bonus matrix for the observables. Now these are QLB is weight coefficient or cofactor matrix for observed quantities. QLB or LA weight coefficient matrix for adjusted observers. Similarly, QXA is weight coefficient for adjusted parameters. QV weight coefficient matrix for residual. Similarly, sigma LA, sigma LB covariance matrix for observed values as well as adjusted observation. Sigma hat LA a posteriori covariance matrix for adjusted observation. Okay. Then sigma XA a posteriori variance covariance matrix for parameters. Sigma hat XA a posteriori variance matrix for parameters U cross U. Sigma V a priori covariance matrix for residual, and sigma V hat is a posteriori covariance matrix for residual. Whenever we are using a priori word, we are using sigma naught square. If where we are using a posteriori, where we are using a posteriori, we are using this sigma naught square hat. लेकिन अभी भी you just need one look. So I'm just giving you a little time so that you can quickly go one by one. I hope it is highly in terms of zoom you can have value. So I'm just again zooming a bit. Although you can also zoom from your side in your screen, there's no problem. But anyways, you just look at this once, because if you are comfortable in writing this, if you were in the class, if you were having this class in offline manner, I usually ask all of you to write on a fresh page, each one by one, the notations. I'll give you these values N, LB, LA. If you do not write, you will not remember, because in the next few slide I'm talking about these notations only. And if you do not know the full name of the notation, you don't understand. You will simply say that what is this LB, what is this LA. If it is better that you should properly have a look and you write it at least once. Do not simply when the class is finished, you do not simply wait for next class. In between, you try to use your revision to make sure that you properly refreshed. Any questions if you are having, just feel free to ask, because it's important that I mean you should you know understand before we move ahead. Any questions from any one of you? Anyways, so with this we stop here, because the another content which we have to teach needs another 1 hour. So we cannot start just for 15 minutes. So with this we stop here. I just